Okay, yes.
I'm curious, if you make a measurement through some sample volume with a laser at some relatively high power, is it possible that you actually excite the distribution?
That's called saturation broadening. So you always want to be in a linear regime. So remember when we have the B12 and the B21s, if you put enough molecules in the upper state, they'll start coming. So you can saturate it. So we assume that when we're depopulating the lower state, that it's a small fraction of the molecules that are there. So you don't want to have too much depletion. Maybe you're okay because the gas is moving by your laser, but if it's sitting there and you send in too many photons, and the fraction that's absorbed is said just by the absorption coefficient, you'll absorb too many photons, you'll pump too many molecules up, and you will decrease the absorption coefficient because you deplete. So this is saturation, and it's a subtle thing because it also leads to distortion of the line shape, because it will saturate at the line center before it will saturate in the wings. And so there's a whole lot of things that come into play once you crank up the laser power too much.
Is there any good rule of thumb?
Well, you can calculate the absorption. You can just decide for yourself if it's a situation where typically we use milliwatt lasers. I remember I've used a few hundred milliwatts. It makes it, if it's passing by your observation window, it's not a problem, but if it's sitting there, well, imagine you have a static cell. This is like my exam problem. Static cell. You have something in there. Maybe it's OH. You send in some light. It's absorbed. And so now this is an adiabatic system. What's happening? You're heating the gas. You're pumping it up to another state. It wants to, you're sending energy in. Something has to happen. So you're heating it up or it's radiating away. But when you really crank it up, you're taking too many molecules out of the absorbing state and you're distorting the Boltzmann distribution. But now this is where it gets into the subtlety of whether it's homogeneous or inhomogeneous broadening. We don't like to go there. So what you do is you just typically make sure, you can calculate it. What's the distortion in the population that takes place? So, and you have to be careful, it's different for an atom than it is for a molecule, but typically you don't encounter this for combustion conditions at atmospheric pressure and higher. If you depopulate a rotational state, its neighbors rush in to help. So you remove maybe a few from J of 10, V equals 0. Well, but there's all these adjacent rotational states and they start helping out. So you put some molecules up here, but they're replaced at a collision frequency, which is 10 to the 10th. So usually you don't have this problem unless you use a very intense light source and it's kind of stationary. But it's a good question. It's a problem you have to at least think about. Typically, if you're worried about this, it's more of a problem in fluorescence. More of a problem in fluorescence. You want to send in as many photons as you can. And if you send in too many, you start distorting the absorption coefficient. So you always check to see that it's linear. We call that the weak excitation regime. You want to be there. So usually you're going to get close to that limit. You just keep cranking up the power if you have some left until you start noticing it's no longer linear. And you back off a little bit. But in absorption like this, I can't even remember ever running into this problem. You could do it maybe if it's some sort of low density, low pressure, static situation, but combustion gas, atmospheric pressure, not likely. Any other questions? Yes?
I guess this would be more for the splitting part of it. Can you comment on the Zeeman effect?
Aha. So yeah, I can comment on it. Can I comment on the Zeeman effect? So when you introduce a field, electromagnetic field, you induce these splittings. And they may or may not be large enough to make a difference. It could be that it shifts the absorption line away from your excitation laser or not. Depends on your. So you could be either trying to study this, but the Zeeman effect, the magnitude of the shift depends on the strength of the field and also specific to a species. So it's an issue. So people have done this. People probably got Nobel Prizes for this. They send in, apply some field, and they measure the shift. And that tells them something very important about the character of that atom or molecule. So it's something the physicists would do to try to study the atom or molecule. Just like we use the positions of lines to say something about the the shape or the structure of a molecule. Another level would be the Zeeman effect. I would avoid it like the plague. I don't think we ever encountered it. Combustion conditions. I think you have to design your experiment to see this. And you can then either use it to advantage or avoid it. Any other questions? Okay, so now this is something that I really enjoy. This is tunable diode laser absorption, sometimes known as TDLAS. Tunable diode laser absorption spectroscopy. That's where the TDLAS comes from. And I've been working on this now for 35 years. And so it's very rewarding to me to see what's happened in 35 years. I'm going to show you. I'm going to start off by this little bit of history of how this has really paid off. My students are currently doing some experiments at the University of Virginia where they're applying this technology to studies of aero propulsion, scramjet combustor. This is a vertical tunnel at the University of Virginia where you can tell it's really hot. It's a scramjet test facility. So I'm going to take you through some history, remind you of some fundamentals and sensor strategies, wavelength access, example. Now, these diode lasers typically work from the visible to the infrared. They typically work from, say, 700 nanometers out to maybe 10 microns. Any one laser will only work in some narrow region, but you can buy them to work almost anywhere between, say, 700 nanometers and 10 microns, the wavelength. Cost may vary, but you can do this. These are mostly row vibrational transitions. One exception being oxygen, which we've talked about here at 760 nanometers. Mostly they're row vibrational, which means the line strengths are tabulated in high trend. It's simple. You pick a line, and you have to understand the notation well enough, but for the most part, you don't go through the exercise that we've just been going through. Except you need to know this in order to decide why did I pick that line instead of that line, and so you have to have some knowledge. But anyway, I've been working on this a long time. I'm going to give you I'm going to end up with a lot of examples to try to motivate you why this is something that engineers can and should do. So I've been working on this 35 years. I'm not sure what's going to come up here now. Let's see. Okay. There's supposed to be a 19 over here. You're missing the 19. You're missing the century. So I started working on this in 1977. In those days, the tunable diode laser was cryogenically cooled. I had the first one outside of Los Alamos. They were using them these were tunable monochromatic lasers in the infrared. They were using them to study isotope separation. It was classified. They had it at Los Alamos. It finally came out at around 1976, 1977. And I had one. And I began to use it to study flames and shock tube flows. It was cryogenically cooled. You had to cool these. It's a materials problem. You had to cool this little chip that's about the size of the pencil lead on your pencil down to, say, 12 degrees Kelvin. So the refrigerator cost $43,000. The laser itself was hard to get, but it wasn't that, They still make those. Those are cryogenically cooled infrared lead salt diode lasers. That's where I started. And then I drifted away from this a little bit because these lasers were so expensive. And I came back to it in 1989 when somebody asked us to find a way to measure the mass flux of air into the inlet of an aircraft. And so you think about that, how can you do that? Well, you have to measure oxygen or nitrogen somehow. You need to have both density and velocity. So I worked on this and I realized we could measure absorption at 760 nanometers due to what's called the atmospheric A band, which is a weak transition, but it's strong enough that there's 2% absorption per meter. And we could, by combining velocimetry with Doppler effect and by measuring the density of oxygen and using the known mole fraction of oxygen, you could get the mass flow of air into this engine. And it worked really, really well. We did that in 1989, got an award for it. And then but this laser was room temperature. And the first laser I bought was $12. Nothing has ever been $12 since then. But that was because they were mass producing them. That was a period of time when they were mass producing 760 nanometer lasers for telecom. Now you have to pay thousands of dollars to get a 760 nanometer laser. All has to do with how many they can make. So after a while, we switched over to water as a combustion product, which would be present at the exhaust of an engine. So if you can measure the mass flux in, which is rho u, you can measure the momentum flux out, which is like rho u squared, and you can measure, therefore, the thrust of a rocket or something like that if you want. So we wanted to go to water. And we started to learn how to measure temperature. So that was around 1990, about 20 years ago. We started working on control of combustion in 1998. That would have been the first, I believe, the first laser-based combustion control experiment that was done. A student is some high-level person at GE now. Once we learned how to measure one species, we finally realized it's not that much harder to measure multiple species. So sometimes we'll measure simultaneously multiple species, different wavelengths, different lasers. Lots of applications started happening around 1996 because it became simple enough to do this. Arc jets, I think I showed that the first day. Hypersonic tunnels, gas turbine engine sector rigs, all sorts of applications, engines, coal-fired power plants, coal gasifiers, and so on. So what I like about this is that the Air Force started to use this technology for oxygen. They might also be doing it for water. And they actually flew this in 2012. So it's 35 years from the time this started till the time it was actually in flight. It's not routine. The spectroscopy is actually pretty routine. Now it's the engineering. How do you put this on something that flies? That's harder. And along the way, we've just done a lot of different experiments, and now we use this pretty often in our shock tube experiments and in some scramjet testing at different places. So that's a nice success story. I remember when I started with lasers, one of my friends was working with LDV, and he was telling me that it was 20 years from the time it was kind of first demonstrated till there was some really pretty user-friendly commercial equipment. It takes time to do these things. But this has been my vision of how this could work in aero propulsion. I don't remember if I showed this on day one or not, but this is kind of a cartoon of a scramjet. And the idea is that you use different colors, different wavelengths for different species and different parameters. And you could probe by optical fiber different places in the engine and measure mass flux and thrust and species and temperature and so on. Or you can measure the health of an engine by measuring the appearance of some metal atom that's coming off the walls that are too hot. So over time, we've learned how to measure a lot of different species, oxygen, H2O, CO2. Now we're doing CO, NO, some other species. Typically, we'll try to understand the spectroscopy, build a prototype, decide what transition to use, measure the line parameters, make sure we have a good database, and then eventually we're ready to take it in the road. And the students will package up this stuff in 3 or 4 or 5 suitcases and take it to some place. And this has been now the last 10 or 15 years, I guess. Okay, so this is kind of the big picture. Now I want to give you some fundamentals of how we think about this. So you imagine a light source of intensity I0. Now these are CW lasers, so you can think of this as just milliwatts. It might be 2 milliwatts, sitting at a single frequency nu, passing across a length L of gas that we usually assume to be uniform. We measure the light that comes out, take the ratio, that's the fractional transmission at frequency nu. Now we can scan the laser across an individual line by tuning its frequency, or we can sit at line center. There's different strategies that I'm going to show you. This would be scanned wavelength, line of sight, direct absorption. And you apply the Beer-Lambert law that we've talked about in terms of the spectral absorption coefficient, or sometimes we write it in terms of a cross-section. So there's the length, the number density, the cross-section. It's just a number, but it's a number that depends upon temperature and pressure. And so you need to know the spectral absorption coefficient, and we tend to write this as S, that's the line strength, S phi, this is the mole fraction, so this is the partial pressure. So I like the units of centimeters minus 2 per atmosphere. So that's just S phi partial pressure. So you measure the fractional transmission, you know L, If you know T, you know S, and you know the line shape function probably, and you solve for this. If you don't know the line shape function, maybe you trace it out so that you know what it is. So we use this technique to measure line shape functions. So my students have published like the first line broadening parameters for, we did this in UV, with the tunable UV. So we published a lot of line broadening parameters. Those 2 gammas for high temperature gases we measure. We use a shock tube or a flame or something like this, and we measure those because they're not really in the literature. We'll split the beam and go through at 2 angles so that now when we're scanning this laser, we see 2 signals, one on each detector, and one they're shifted by the Doppler shift. We can measure the velocity. So my point is that these lines, these shapes and shifts contain useful information. They depend upon the temperature, the velocity, the pressure, and the broadening and the mole fraction. Temperature is always important in combustion and chemistry, so we usually get that by taking the ratio of the absorption in 2 different lines simultaneously. If we use 2 detectors, sometimes we use 1 detector, but we either dither back and forth or we do some tricky modulation schemes. But these are 2 different lines, meaning that the absorption is from 2 different quantum states of the same species. The ratio of those is the ratio of the Boltzmann fractions, which gives us temperature. That's how we get temperature. And you have to be intelligent about how you pick these wavelengths and these transitions. Once you learn how to do a couple of these things, you can do more. Might do 3. I think 5 is maybe the most we've ever done. Hard to get 5 things to work at the same time. You can use this to do multiple species or multiple parameters. Now, you can also split the light and measure at the same wavelength, but 2 or 3 or 4 or 5 or 10 locations. So that's a different problem. But just right now we're talking about 1 line of sight. If you have non-uniform, which is the biggest question you always get is, well, how do you know it's uniform, or what happens if it's not uniform? That's the biggest problem. It is a path integral measurement. But if you know the distribution, that is, maybe you know it's parabolic or something, you can use that to advantage. Or you can make measurements at different quantum states of the same species, which means each one will have a different temperature sensitivity, and you can unravel to some extent the spatial non-uniformities. But that's a problem. So usually we design around it and we try to pick wavelengths that are insensitive to this. Yes?
Could you use like a tomographic technique too, and so
Sure.
take it in basically the same way?
Yeah, can you use a tomographic technique? Sure, well, that's what I just said. You can split the beam and simultaneously measure on some number of beams. Now you may have to have optical fibers cheap, but you may now have to have 10 detectors if you want 10 beams. But it's the same physics. So if the laser beam is powerful enough, and if you have the need to measure this in multiple places, you can do this. You can construct your tomographic beams in different geometries. But yeah, people do this. But the physics is the same. And you have to understand the physics to get this optimized and get it right. Now there's 2 main strategies I'm going to tell you about here. The first one is scan direct absorption. That's the one I just told you about. We modulate the laser wavelength, usually with either a sawtooth of current through this junction or with a sine wave. So you vary the current through the junction, which varies the wavelength. You basically are heating up this little thing, it's changing the index of refraction, it's causing it to tune in wavelength. Unfortunately or fortunately, that also causes the intensity to change. So when you change the current, the amount of intensity that comes out changes at the same time the wavelength is changing. So when you scan over, say, a millisecond or so, and by the way, we can scan at 1 kilohertz, 10 kilohertz, 50 kilohertz. What happens with time is you see the intensity changing, there's the absorption line, there's another one. If I fit this baseline, we call it the baseline, call that I0. I can take I over I0, replot this as the absorbance, and now there's my individual line. That's often what we try to do. So one problem with this strategy is that what's the minimum absorption that you can detect? It's usually limited by how well you can decide what I0 is. And that might be 1%. The nice thing about this method is it's almost foolproof. If you can get a strong enough of signal, you scan across this absorption line, you can immediately do the integral, and it's independent of line shape. It's just, you've just measured the number density in that state, assuming you know the line string. So it's almost foolproof if the absorption is big enough, meaning more than a few percent. But there's times when the absorption is not big enough, or we have some other problems. And so we've developed another approach. It's called wavelength modulation spectroscopy, WMS. And you superpose on this current waveform a high frequency sine wave at frequency F. So now the detector sees this fuzzy stuff plus the absorption line right there. So now you can ask your computer, nowadays they use the computer instead of a conventional lock-in amplifier. You can ask the computer to give you the signal at frequency F or 2F or 3F or 4F. And if you ask it to give you the 2F signal, it's kind of like the second derivative of this line. But there's some question about whether you can make it all positive or negative. Looks like right here, I've allowed, okay, so this is like the second derivative, but you can do it in a way that the signals always come out positive. So this, roughly speaking, this is the second derivative. It has the virtue that this signal is 0 in the wings. Always easier to measure deviation from 0. Up here, I got to measure the deviation from an I0 that's not that well known. Now down here, I just can measure the deviation from 0. It's a clean problem. So this method can be 10 to 20 or more times more sensitive. And I like to say it's also 10 to 20 times more complicated, because we're dealing with some electronics and you have to be careful. But it turns out this method has some advantages that I hadn't fully appreciated. Because you're sampling this signal at 2F, and I'll tell you in a minute why we do 1F. You're sampling it at 2F, you're only looking at the frequency content, the signal content near this F. It means you're not looking at low frequencies. Any low frequency noise is kicked out. It has big advantages for noise rejection. Turns out, I thought we had a problem, and I realized it was an opportunity. Because this is changing, we can divide by the slope of this line, which is essentially the 1F signal, and take the ratio of the 2F signal and the 1F signal, and it's insensitive to laser power. They're both proportional to laser power. Take the ratio, it's insensitive to laser power. So all of a sudden, if my window's getting dirty, the laser beam is fluctuating intense, all that's canceled out. Amazingly powerful idea, and I'm going to show you this here. We discovered this, I don't know, maybe 5, 6 years ago. So now let's imagine we have a modulated tunable diode laser at 1.4 nanometers, which is where water absorbs. We pitch it, we call it pitch and catch. We pitch it across some gap. Looks like the gap was about a foot. And the ambient water gives us, what is that, 5% absorption? So we're going to see about 5% absorption just in the air, room air. And we're going to demonstrate what happens when you attenuate the beam. So here's the case where we have the signal. This is the 2F signal. And with time, what the student is doing is he's blocking the beam with a razor blade. He's just kind of sweeping a razor blade across here. That blocks the beam and causes the 2F signal to go down by about 60%. But the 1F signal goes down by 60%. And if I take the ratio, it's constant, which shows that even if the signal, the laser intensity was fluctuating on me, blinking away, the optics are bad, alignment's bad, I just process the light that comes out and take the 2F over the 1F. That's really an important idea in real systems. Now the student then pounded on the table, and so higher frequency stuff, but the same effect. You get some transients in 2F, transients in 1F, take the ratio, it stays constant. This is a really powerful idea for a lot of practical applications. So let's see, I don't know if I'm going to show this or not. One student used this in a highly scattering environment in a coal gasifier, and the transmitted light, I think, was only like 0.01%, 10 to the minus 4. We still got what we wanted. So it's insensitive to the absolute amount of power because it's only looking at relative signals. Now, what kind of wavelengths can we cover with this kind of technology? And what species do we care about? So if you're an NO person, This is wavelengths now. These are the strengths of the transition. At 700 Kelvin, 1 atmosphere, 1 centimeter path length. I can't really read these numbers. Vertical is stronger. So NO has, this is the so-called, what is this band called? Delta V of 1. Give you a clue. What's that called? It's called the fundamental. What's this one then? Let me give you a clue. It's at half the wavelength. First overtone. Second overtone. Notice how it gets weaker and weaker. CO, from here to here is 2 orders of magnitude. Here to here. So if you can move over to here, you've just gained 4 orders of magnitude relative to where you started. Maybe you don't want to be here because it's too weak. So these molecules have different absorption bands. It gets a little more complicated when they're polyatomic. Water is virtually everywhere. That's a plus and a minus. It looks like it's everywhere, but in fact, if you blow this up, there are big gaps. But water is everywhere, so it means that's an opportunity for combustion product measurements. Fuels are always absorbed down here around 3.4 microns. But now the difference between the fuel and these small molecules have discrete spectra. So if I blew this up, you see all the lines are completely separated. The fuel, on the other hand, is like a broad featured structure. You have to use a different strategy for that. You have to use a different strategy for these blended absorption features. Okay, what wavelengths can we reach? Well, here's from, say, 0.4, 0.5 microns in the visible out to about, now this should be out at 10. You can get out to 10 or 11. We had a laser at 11 microns recently. When you change wavelengths from here out to, say, 10 microns, you have to change materials. And so the structure and the design of these lasers changes. The telecom is kind of in this region. This is the highly developed, mature, relatively economical, robust stuff in optical fibers. This is, I'll call this emerging, but they're at various levels of maturity. You can now buy lasers essentially everywhere from here to 10 microns if you have enough money. And they can be cheap or they can be expensive, but it varies. So these are just some of the molecules we might measure. Now, we might be interested in combustion, but they could be doing this. I have students who do this with aircraft testing. I mean, they'll fly something and sample in the atmosphere. A lot of different people who are looking at isotopic ratios for biomedical instruments. It's the same process, same physics. So the nice thing about these visible in this region here is that the fibers are well developed. So you can imagine propagating the light by fiber to the experiment, splitting it, collecting the light, taking it to your detector. So you might want to isolate your equipment away from some nasty experiment. Let's look at lasers and detectors. So they typically look something like this. They can be little things. They might be in the price range of $1,000 to $6,000. You can buy them fiber coupled so that they're easy to use, up to about 2.3 microns. There's something called a quantum cascade diode laser. That's QC. They're emerging. They can be up to $40,000. These things are typically 1 to 500 milliwatts, depends. Like I said, we tested 1 to 11 microns recently. It's possible to get down to shorter wavelengths, but usually it's accomplished by frequency doubling. So they can be compact. If they were mass produced, they'd be cheap, but they're not really mass produced, and so they cost you. But they're very powerful. So now, what did I hear? Some of these lasers can tune only a short distance, and others can tune farther. The so-called external cavity diode lasers can tune over 100 wave numbers or so without any trouble. Actually, the one we had the other day from some company tuned much farther than that, tuned over microns, but not continuously. It only works in some places, and so that's not yet perfect. Some of them require cooling, some don't. Some are pulsed, some are CW. Usually what happens is they figure out how to do this first with pulse lasers and cooling. And you hope that they'll eventually be CW lasers without cooling. Maybe just thermal electric cooling. It's a materials problem. You have to build these materials such that there is a junction and a band gap that's in the right range. And so there's different, it's kind of a materials problem. What kind of detectors do you use? two primary types of detectors. Well, there's photodiodes and there's photovoltaic. As you change wavelengths, you change the detector you have to use. So you might use silicon detector out to 1.1 microns, and we might use indium antimonide out to, that says 7, but usually it has a sapphire window. You can only use it out to about 5. Or here it is, indium antimonide 77. So why? Because these are quantum detectors. They're trying to respond to an individual photon. And the photon comes in, it has so much energy. And you have to have a band gap that's compatible with this. There has to be enough energy in the photon to create an electron. Simple model is, let's see, is it on my next slide? No, okay. Simple model is a photon comes in and it has a certain probability of being converted to an electron. That's called the quantum efficiency. Might be 10%, might be 90%. Let's just say it's 10%. You've got to send in 10 photons to get one electron. The electron then just flows in the circuit and you measure the voltage. So the photovoltaic, a real simple model, photons go to electrons with an efficiency of, say, indium antimonide, they can be up to maybe 50, 60%. So, but they're quantum devices. Quanta give you individual electrons. That's in contrast with a detector that was based upon heating, like a thermocouple or something like that, bolometer. But when you get out to the longer wavelengths, out here, the long wavelengths, let's say you want to work at 10 microns, 20, you got to use some pretty exotic materials. Price starts going up. I think we pay around $6,000 or maybe 6,000 euros, I can't remember, for a detector out here at 10 microns. They're cooled, liquid. Everything's harder because those photons don't have a lot of energy. And so you got to have a really nice detector. This is here in your notes. You can take a look. So you care about their responsivity at your wavelengths. Here's our Mercat telluride. You also care about the bandwidth. You say, I need 10 kilohertz or 100 kilohertz or megahertz, or you're going to respond to an individual pulse of light that's 10 nanoseconds long. You got to have a very fast detector. That has to be made differently than a slow detector. So, and that may affect the size. So there's some trade-offs in detectors. The materials, the geometry, and the bandwidth have to be considered. Most of the stuff we do is with CW lasers, and therefore we don't need, we typically are satisfied with 1 megahertz bandwidth. Detectors are characterized by something known as D star. How many people know what D star is? Nobody, okay. D star is basically a number divided by noise equivalent power. You want big D star. It's a measure of how good it is. And it might say that it's 10 to the 11th. And this D star depends upon the square root of the area and the bandwidth. So if you have a certain D star, then that determines the value of this. And there's some trade-offs then between A and delta F. Or you might just be interested in a small value of noise equivalent power. So the bigger the D star, the smaller the noise equivalent power that you can detect. Okay, I'm now just going to spend time on examples. So just a lot of examples that will hopefully motivate some of you. Let's see, I'm going to talk about velocity measurements in a, yes?
So you did mention like a spectrometer in your detector. How are you then like knowing what wavelength you're at when you're...
Okay, so there's a couple of reasons. Okay, why don't we have a spectrometer? Well, the lasers are monochromatic, so we know that there's only one color. We don't have to have the spectrometer to filter out the ones we don't want. We mostly care about the change in wavelength, not the absolute wavelength. So we have a little box that's called a wave meter. We send some light into the box, it tells us the wavelength. It'll tell us to several significant figures, so it's not a spectrometer, it's a wave meter. That tells us the nominal wavelength. But usually what we care about is, are we at the center of, or are we tuning across an individual line? So we'll turn the thing on and we'll say, I want to be at 4.296 microns. Turn up the current or change the temperature, you get it there, then maybe you start tuning across that line, and in your experiment you can see that you're encompassing the line you want. So we don't use a spectrometer, we use a wave meter. Sometimes the lasers are so stable, you can set it at the line center and come back tomorrow, it's still the same. But anyway, we use a wave meter instead of a spectrometer. So I'm going to show you a lot of examples here of different kinds. A lot of them have to do with, actually the first one's subsonic and the rest are all kind of supersonic. We did this in a wind tunnel probably 10 years ago. So the goal was to try to, this was in, to get ready to measure the velocity at the inlet of a Pratt & Whitney engine. So we're doing this in a wind tunnel where we could produce known velocity, and the question is how accurately are we measuring it? And so this is the Doppler. So when you have the so-called split beam concept, here's the, you can use one color or two, but they are split so that one goes forward and one goes backwards. And if you look at the positions of these lines, what you find is one is upshifted and one is downshifted, and all I have to do is measure the spacing between the two peaks. Actually, this was water, so this was a little later. First we did oxygen, then we did water. Okay, this is what we got. This was the tunnel velocity, and the velocity we inferred from the Doppler shift of the two features. So we measured the absorption line for both directions. And you see that they're spaced, separated. And the question is, well, how accurate is it, and how small a value could we measure? So here we only could go up to 18 meters per second in this Professor Bradshaw's wind tunnel. So the idea is, there's some uncertainty in the velocity, but he's been working with this a long time. So he tells us what the velocity is, we measure it. And it was just like right, dead on. I don't think we actually have a point at 0, so I'm not quite sure that's there. I believe our lowest value we had, the lowest value we had was I think 1.8 meters per second. I think he's just locking it down there at 0. Looks pretty good. That's not saying that this is the best way to measure the velocity in a subsonic tunnel. It's just saying that it works. And we check it near low velocities, and then we have confidence in it at high velocities, because the signal gets easier. Okay, he claims half meter per second precision. Now then we went to NASA Langley, where our goal was to make a measurement in this big beast. This is a case where they're interested in testing scramjet combustors. And the way they simulate what would happen in the atmosphere at high speed is on the ground, they heat some air, and they heat it, and that's called vitiated. And then they expand it to say Mach 2.5 or 3 or 4 or 5. And then they send it into the engine. So there is this combustor is the place where they would put the engine, and then they would diverge. This isolator is this kind of entry-level section where we're going to make our measurements. The nozzle was the exit of the heater, so that's the thing that prepares the air to simulate flight at some Mach number. I think they were testing at Mach 5 and 7. See what it says here. Okay, it's a Mach 2.65 nozzle, which exhausts the gas at 990 Kelvin at 0.7 atmospheres. But that simulates Mach 5 flight, because in the supersonic scramjet, it's flying at, say, Mach 5. The air is coming in at Mach 5, but then the air gets heated up, and its Mach number when it enters the engine is down by a factor of 2 or so. So the local Mach, so you have to simulate that right here. So that was the condition. He built, the student built some translation stages here so he could scan in a plane, and he could move the plane up and down, and he could move it across. So not at the same time. So he could scan in a vertical plane in a second or two, and then he'd have to switch over and he'd scan horizontally in a second or two. So the idea is you'd map out what you can see with this line of sight method. From this, you get the velocity, the temperature, and the mass flux. So here's this translating sensor. And so you have to have windows. You have to have pairs of windows because the light comes in at 2 angles. In this case, he didn't have cross beams. He had, did he have a perpendicular beam? He only has 2 beams. He needed 2 windows. There's his scan. Well, he could do the scan in one direction quickly, but then it took some time to change it to go the other way. This thing would run for a little while. Here's his results of, this is the distance from the center line. So there's 0. And let's see, this is I think that's the vertical scan. So when he's scanning vertically, This is the velocity profile he'd mapped out. So there's the boundary layer and there's kind of a flat region. His highest velocity was 1,500 meters a second. So we were kind of curious, how non-uniform is it? What kind of velocities does he get? He did the horizontal and the vertical. One thing we hadn't expected is, since they would only run this thing for, say, 20 seconds, we could see the transients. We could see it ramp up and go through a hiccup and then the shutdown. We could see things that their other instrumentation couldn't see. So we've taken these ideas now to the University of Virginia, where the students have been 4 or 5 times. This is a smaller tunnel. The Langley Tunnel is kind of a big deal. It's like a huge, monstrous facility. This is a small university tunnel. This is about, I don't know, inch across here, maybe inch and a half. They have electrically heated gas at about 1200 Kelvin, total temperature, 770 static temperature. They pass it over a fuel injector, a ramp and a fuel injector, and they want to know what's happening down here. We usually bring in different colors of light on some, okay, this is, Y is the distance from the injection wall. X is the distance downstream. So X over H is the number of ramp heights downstream. And then Z is the direction into the panel along which we make our measurement. Now, we use 2 colors. We're trying to get temperature. We scan in Y. So we're measuring along the path integral on Z, but we scan in Y pretty fast. And we move downstream and do it again. The real question is, what's the implication of the non-uniformity of this flow field? This is a non-uniform flow field. So we appealed to CFD from North Carolina State. And this is the projected water, total amount of water. I think that's called water density as a function of Z. So this is along the line we're looking. We're looking along Z at a given Y and X. So the water distribution calculated looks like this. So what happens when we measure across this? What do we get and how do we interpret it? We get some sort of path integral. We get some sort of path average. And so the question is, how do we relate this to the CFD? So we learned that the way to do this is, what can we do about this problem? We decided that we'll call this the column density. So we measure along this line, and we measure the path integral, total amount of water. And the trouble is, the absorption, it depends on the line shape, and the line shape is varying along this line, and that is kind of a problem for us. So we basically integrate over the line, and we end up with something that is related to the area. This is the CFD water versus distance. And the total amount of water along that line is what we measure by our strategy. So we introduced the idea of column density, total water in that column. And now we're going to compare with CFD on that quantity. We do the same thing for temperature. I won't get into this. So there's some subtleties of how you interpret data for non-uniform flow, but we're learning how to deal with this. And now we've conceived of what I call the species-specific temperature. So we measure, if we're measuring water, we only get signal from water. And we only get the temperature from water. So we get the total amount of water and we get the average temperature of that species water. And so now we know how to do this for different species. And I think this is probably a pretty good idea for finding a way to compare with CFD. So whenever the flow is non-uniform, you have some problems that you have to deal with. Otherwise, this works really well. I want to show you how well it works. This is our column density idea. The absorbance, here's the Beer's law. Since it's non-uniform, you have to have e to the minus the integral of k nu dx. Here we are. Here's s feet. I'm going to write it in terms of density instead of pressure. And if you pick a line such that the line strength goes as 1 over t, this t cancels this t, and now you've got a measurement. The integrated absorbance under this line is proportional to the total water along that line. So that's one of our strategies. We can report out the total water along that line, and then if we measure it along all the lines in that plane and combine it with velocity, we have the flux of that species across that plane, and the water flux can be compared with the influx of fuel to get the combustion efficiency. So So I've just said a lot in those few words, but I think this is a new way to test CFD using our simple method in a non-uniform flow. It's not spatially resolved, but it's CW, it's quantitative, it's easy. How else can you do this? Well, you might say, why don't you use PLAF? PLAF may give you the information, gives you the spatial distribution, but it's not quantitative. And you can't do it for water. So you can't do it for hydrogen. So you might say, well, I'll use single point Raman. That's fine, except that the guy that does that, he's there for about a month. We're there for like 2 days. It's a long time to gather all that data if you're going to do point measurements. So anyway, that's what we've been doing at the University of Virginia. I think it has a lot of potential for dealing with non-uniform flows in comparison with CFD. So I'm going to show you some comparisons. So this is now a plot of, this is distance downstream from the injector. That means that's distance, that's distance from the wall. Okay, one of the walls is angled out, so we actually measure the distance from the opposite wall. This is the injector side. This is distance from the injector wall. This is the column density of water at a given distance downstream of 18 heights. The dashed line is the CFD, the symbol, diamond symbols are our data. So I don't know whether you'd say that's good or bad. It's pretty good. We get it pretty good in here, but there's something fishy going on right here. And I just don't know whether we're a little bit wrong or they're a little wrong. There's a lot of fuzziness in both. But we think that the water is penetrating further than they're calculating. If we do this at another distance, this is 12 heights downstream, we get the same pattern. Pretty good agreement. And then we show the water, we say the fuel is penetrating more. This is hydrogen fuel. We say the fuel is penetrating more than they think. And so on, 18. Temperature is the same way. We get pretty good agreement here on the fuel wall, and then it looks like it's too high, which is consistent with this. We think the fuel is getting out farther and burning more than he computes. That's Jack Edwards at North Carolina State. So it's both good and not good. It's good in that it's pretty close. It's bad if you're expecting it to be within 5%. This turbulent combustion is not a simple thing to calculate. A lot of problems. Now we did velocity also. This is pretty good. So we use our cross beam idea, and now we're measuring water. So what we're plotting is the axial velocity of the water. This is the distance from the injector wall. Here's our data. By the way, the free stream is 950. It's way up here. This is the velocity, the free stream. That's the known velocity. This is pretty good. This is pretty amazing that the calculated water velocity and the measured water velocity are so close. It's really pretty impressive, I think, because we measure this in a short time. So we can combine the velocity of the species with the column density of the species to get the flux of the species, measure it at different lines, and we can say, past that plane, what's the flux of water, amount of water per unit time. I don't know any other way to get that. And this one's really spectacular. So we go at a distance of x over h of 6. I mean, we even get this little dip here. So you got to remember, the free stream's out here at about 900 meters per second, 950. And we're tracking this down all the way down to about 100 meters per second and getting this dip. So we're able to get velocity pretty darn well. Now we took the same idea to an impulse facility called ATK, that's in Long Island, New York, where they can test at Mach 10. That means they only test for a few milliseconds. It's a combustion-driven tunnel, reflected shock tunnel. They can get up to about Mach 25. And so it's a detonation-driven shockwave experiment, but they only have a few milliseconds of test time. And their test section is really small. Let's see if I got this here. Okay, here it is. Their test section is about 1 inch high. I think it's a little less than 1 inch wide. And so we split our beam into 3 parallel beams, little teeny beams. And we looked at one distance downstream to see what we would see. This is what they compute for the distribution of water. And we're looking along these cross sections here. So we're not going to be able to resolve that, but we were optimistic. So Mach 10, to get to Mach 10, you have to have a pulse facility. Pulse facilities mean they're not so well characterized, they're not steady. It's a difficult thing to do, but it's the only ground test way you could do this. We're going to try to measure water and column density. Bottom line is it didn't come out as good as we'd hoped. Now the question is why? I think our diagnostics were working and the tunnel's not working that good. So the way they compute it with the time zero is this is a window, 3 millisecond window, where they should have what they want, hopefully. This is the column density versus time at a given location, equivalence ratio of 1, particular angle of attack of the engine. And this is the value that the CFD says we should get. What we get is something that looks like about 2/3 of that number that's drifting up. So it's not producing, we say, it's not producing the amount of water that the CFD says that facility should get. Who's wrong? Or what does it mean? I would argue that you need this kind of instrumentation to characterize this facility so that you can ever believe anything. Here's the temperature. This is the free stream temperature, and the elevated temperature is right here. We see only a little bit of increase. So the good news is we're measuring within, I don't know, maybe 50 degrees. The bad news is it's not agreeing exactly with the CFD. So the tunnel people aren't real happy. The CFD people aren't real happy. And we wish that they agreed better. I'm not sure. We're happy that it worked. It wasn't easy. By the way, you go there, they were like 2 weeks, and they only gave us like 4 tests. So it was brutal on the students. Because these pulse facilities, they don't get them running right. They finally get it running, you get 1 test. It takes 2 days to get ready again. Not good. We see evidence that this water, you might think that the water should be kind of zero and it should jump up here. We see this early water that they don't like. I think that means that their tunnel, which is combustion driven, is somehow leaking out water into the test gas more than they think. We also see some fluctuations that's telling us something, that the signal's not nice and flat. A few years ago, I had a student who went to Wright-Patterson Air Force Base. That's Greg Rieker. He's at the University of Colorado now. I guess it's been 6 or 7 years, 6 years. He was the one who, he had this under control. He was using 4 lasers, 4 different colors, 2 kind of close together, 2 another up here, propagating through single mode fiber, going through the combustor onto 2 detectors. How did he do that? Well, he modulated at different frequencies so that he could actually use 2 detectors to get 4 signals. And the idea was to characterize this combustor. What does it produce? What does it produce? And we wanted to measure temperature and water. And what we learned was that this flow is not steady. So he grouped 2 of his lasers together to be sensitive to water at high temperatures, and 2 of his lasers to be sensitive to water at low temperatures. And if everything is uniform, they're the same. They are right here. But he's picked out a sample of time from 30 to 55 seconds where they begin to drift apart. How can that be? What we decided was that the flow was beginning, the early stages of what's called unstart. It was beginning to become non-uniform. So it was nice and uniform, and all of a sudden it starts to unstart, and these 2 temperatures drift apart. And at first we were trying to understand the difference in temperatures to sort out the non-uniformities. And then we realized that there was something better to do. And so what we did is if you look closely, you'll see this one looks noisier than this one. So we did a running FFT of these 2 signals. And what we found is that in this region here, the low frequency content of these 2 signals was about the same. But once you get out here, you begin to realize this one gets noisier than this one. And so at that point, which is right here, what we found is that when these unstable events began to occur, we could see it. The red is what happens if we don't have that. So suddenly we realized it's not so much the magnitude of temperature difference, it's the fact that the frequency content changes that could be used as an indicator of unstart and could be used as the basis of a control system. I think we're beginning to see that frequency content of signals can be used for sensing and control. And that's, all of a sudden we're asking the frequency content, not the value of temperature, it's the frequency content. That was like a new idea for us, fluctuation sensing. I think that's a good idea. So let's see, I'm going to try to finish up. So I think that in aero propulsion, there's energy sciences and there's aero propulsion. I think in aero propulsion there's just a lot of opportunities for this stuff. Industry needs to pick up some of this stuff. Tunable diode laser sensors for temperature, velocity, species, mass flux could be used for characterizing these exotic ground test facilities. You know, they use pressure gauges. That's not enough to characterize these flow facilities, these impulse facilities. I think you're going to see this in flight systems eventually. We're pushing into new wavelengths, new species. We've been using this in detonation engines. I believe we could do this to characterize rockets. So each one of these things has its own challenges, but the underlying physics is exactly the same. It's line of sight absorption. We're working in the infrared where the line strengths, you just look them up in tables. Now okay, I guess I'm going to talk about this next. So next time I'm going to talk about applications in energy conversion. We're going to go into some energy conversion devices and do some of the same stuff. Okay, any questions? Yes?
Do you ever do experiments where you park at the line peak?
Yes, do we ever do experiments at fixed frequency? So if we want to do megahertz, we basically park at the line center. But you can still do 2F, you can still do 2F or 1F, but you park. So in our shock tube experiments to measure species, we park. So we know enough to be sure we're at the line center and we measure the real-time absorption. So that is nice and simple. As long as the absorption, as long as shape is staying constant, it's got a simple interpretation. So we usually either do fixed wavelength or scanned wavelength. Those are the two. And we either do direct absorption or WMS. Kind of like four possibilities.
So when you park it, do you use a reference cell to keep it?
So if when we park it, do we use a reference cell? Really, it depends. If the laser is rock solid, I0, we don't need a reference beam. But if it's unsteady, so if the laser is the source of fluctuations, we have a reference beam and we take that ratio to take out the laser fluctuations. If, on the other hand, the problem is in the windows, that doesn't help us. So it kind of depends on what the problem is. If we have a fluctuating laser, we always use a reference beam. We use two detectors, take the ratio. That takes out the problem. The WMS method automatically takes care of this problem for us. But we can't quite do that at megahertz. We might modulate at, say, 200 kilohertz, but then we have to have fast detectors. So if we only want to work at 25, maybe I'm going to show it next time, I can't remember. We measure temperature at 40 kilohertz, I think, using WMS. So if you're happy with, say, 10 kilohertz, 20 kilohertz, we can use WMS at fixed frequencies to get rid of this window problem. But it just depends on whether it's a laser fluctuation or a window intensity scattering problem, different strategies. But sometimes we park. Yes?
So with the WMS, does your line shape function change?
So with WMS, does the line shape function change? It depends on the problem. Let's say that it does. Then you have an issue. So the nice thing about scanned wavelength is, let's assume it's uniform. The thing about scanned wavelength is, you get the integral, it's independent of line shape. Unless you're trying to measure. The sensitive way to measure temperature change? Could be. So it's an issue. If the line shape changes, what do? Well, you integrate it out or you take it into account. You can scan over it and measure it. So the way we have measured all the broadening parameters, and we've measured, we were probably the best at measuring high temperature broadening. What's 2 gamma of NO in argon at 2,500 degrees? It's only our data. How do we do it? Heat it in the shock tube, scan it over the line, we measure the broadening. So we know what it is, but your question is, what do you do when it's varying? Well, that's the problem. You have to deal with it. So you either scan over the lines rapidly so that you only get the integral and you don't care about the fact the line shape function is changing. We only want the area. Or you have to deal with it. Hardest problem by far is what do you do when it's spatially non-uniform? That's the hardest one. Fluctuations we can deal with. And again, it's a problem or it's an opportunity. You just have to be aware of it. Yes?
You measure the velocity, the speed of the water, right? The speed curve. So I'm wondering, you just compare your measurement with CFD simulation, right? Do you have other benchmark measurement?
We have, yes. So the question, I think, is do we have reference or benchmark measurements for the velocity effect? Well, we measure what it is. And I believe in the Doppler principle. So I believe there's no doubt about the Doppler principle. So if it's spatially uniform, and if we do it in a way that we have forward and reverse beams, we're only measuring the separation. We're not measuring any absolute frequencies, only delta frequencies. It's pretty reliable. So what is how do we check ourselves? Well, we especially like to check ourselves near zero. When you reduce the velocity to zero, you better have the signal go to zero. And now the trouble is, how do you do a reference experiment at 10 kilometers per second? It's a hard problem. So I would say we can measure it better than any facility can calculate it. But that's an issue. Well, when we went to Wright-Patterson, when we went to Pratt & Whitney, we did the inflow mass flux. We agreed within 1% of all their pitot tubes. So there are those kind of experiments. But I believe, you have to be careful about how you measure frequency. We have some etalons. But it's pretty reliable, pretty simple. The biggest problem always is how do you deal with non-uniformity? That's the subtlety. If it's a uniform flow, you're okay. But if it's not uniform, you have to think about this. You have to avoid you have to avoid edges. Yes?
How do you extend this technique from point-based to planar-based measurement?
Okay. How do we extend this from point? What I think you mean is along the line, a single. How do you extend this from one line to many lines? Well, we've done this by scanning one beam this way. We've also done it by splitting the beam. The one I showed you from ATK, we do 3 beams simultaneously because we only had a couple of milliseconds. If you have enough power, you can split the beam into as many beams as you want, but you have to buy a detector for every beam. So one of my students has done some tomography. I think they did 50 by 50 in an augmenter. But the physics is what I'm trying to teach you about the physics. If you want to go to the trouble, you can make 10 beams. It starts looking very unwieldy, but you can do 10 by 10 or 10 or whatever you want.
I'm more thinking on the lines of, let's say, LDV supposed to PIV, where you go
Okay.
from point-based to planar-based.
Point-based to planar-based. Well, maybe I'm going to show you something. How do we go from point-based to planar-based? I'm going to show you when we talk about planar laser-induced fluorescence. I'm going to show you when we do fluorescence that we do point-resolved measurements, both in a point or in a plane. I don't know if I have those results. You can do fluorescence with spatial resolution and some temporal resolution throughout a plane or at a point. But with absorption, it's a little tricky. It's easy to assume it's uniform. Look how powerful this is, if it's uniform. Now, in many applications, you would like actually to measure the integral. Let's say you want to know how much NO is coming out of your power plant. You don't want a point. You want to know what's the path integral. So there's times when this is a plus and there's times when it's not what you want. If you want to study turbulence, this is not the way to do this. But if you want to study how your power plant works or some fluxes, I like this idea. What is the flux of water past this plane? That's a lot of information. That's the total flux coming past this plane. You can't do that with PLAFs. You can't do that with Raman. And you can't do it, and the PIV people or the can't do it without adding particles. We're not adding any particles. So nothing's perfect, but I think this method, first of all, is fairly simple. People can learn this within a year or 2 or 3. It's fairly economical. You can put it in suitcases and take it somewhere. I think it's really, you can't take your pulse laser system with PLAF very easy. So nothing's complete, but this is, I think, very powerful. You could use this for breath analysis, aircraft, rockets. It's the same, and the physics is the same. Yeah, question?
It seems like beam steering is never a problem with this type of
what?
Beam steering.
Beam steering, okay. What about the beam steering? When we do our shock tube experiment, it's always, the problems are always the same. It's beam steering, interference emission, interference absorption. They're always the problems we have to deal with. Beam steering, the light's going across, high pressures, high density gradients, the beam moves around. You have to have a hole on the other side that lets the light go out. And you have to have optics that collect all the light. So we deal with this. If the path is short, density gradients are low, it's easy. If it's a lot of beam steering, we have to pay attention to this. And there's tricks, a lot of tricks. Biggest trick, you have to get it out of the experiment. So it's a chamber, you have to get it out the other side. Whole aperture has to be big enough. Then you have to collect all that light. The easiest thing to do is you collect it, put it into an integrating sphere, you always capture all the light. But you only transmit a little bit of it. So, but the beam steering, I told you the other thing is, my 2f/1f scheme cancels it out. I don't care. The photons that come out, the 2f/1f, I can interpret. Very powerful idea. So beam steering or windows that get dirty with time, 2f/1f.
If you are looking for temperature and you have a temperature gradient in the probe, how much information can you extract just for the fact that they are Boltzmann distributions, and when you do the ratio between different lines, you're going to get a different temperature? Like how much information on the gradient can you get?
So what about temperature non-uniformities? My favorite saying, well, one of my favorite sayings, problems are opportunities. If you have a problem, then you got to deal with it. If you know that it's parabolic, I only need a couple measurements to tell you that temperature distribution, assuming it's steady in time. If I don't know it's parabolic, then we do tricky things like we'll use 10 wavelengths. Each one has a different sensitivity to temperature, and I can tell you over that path, if the mole fractions are constant, I can tell you what fraction of the path length is at each temperature bin. If I bin it between, say, 1200 degrees and 1600, if I know those are the bounds, I can tell you what fraction is in each 50-degree interval. In principle, we've done it. But it's not, you know, it's a hard thing to do. I can't tell you where, if it's cold, and I can tell you if a cold spot appeared, but I can't tell you where. But I can tell you it appeared. What if you're worried about some hot spot or some cold? I can tell. So that's a good question, but you know, it's both a problem and an opportunity, depends on the situation. The bottom line is we measure a path integral. You get the benefit of that and the curse.
So what about the dynamic range? So if the concentration changes quite a bit within the experiment.
Good. What about dynamic range? So the nice thing about absorption is, I told you the minimum percentage absorption we can usually detect is, say, 0.1% in a shock tube experiment. And we don't like it to be more than, say, 60. So the dynamic range is 600. If you say, no, I want it to be 100 times more sensitive, I've got to go to a 100 times stronger line. Too sensitive, I go to a weaker line. Oh, but I want to cover all the range. Then I use 2 lines. So, you know, there are solutions, potential solutions to these problems. It's pretty hard to find an instrument that works over, say, 3 orders of magnitude. But we can get close with 1 line. Any more? So we'll talk more about this on for energy conversion tomorrow. Tomorrow.
Yeah, I just wanted to make a comment. When you